Hi everyone, and now we are ready to start the lecture program of the school. And the first speaker, as you may expect, is a famous professor, my boss, a director of AI Center at Skoltech, Evgeny Burnaev. So please welcome him.
Okay, so by the way, is it possible to remove this? No? Huh? No, so it's not possible to remove the video, right? No? Okay. Okay, so guys, today I'll make a brief overview of some, things related to generative AI. So first of all, some introduction and some comments about the current trends in generative AI. As you know, in recent 10 years, there were a lot of fascinating developments in AI. Namely, everything started from AlexNet in 2012. But then AlphaGo appeared, and thanks to attention, nowadays we have what is called ChatGPT and all these large language models. And so what is so important about ChatGPT? Why ChatGPT is so different from standard machine learning models? Actually, first of all, ChatGPT memorize data. Because standard machine learning models, for them, it's not very good if they really memorize data from training sample, right? Usually this is called overfitting. And if it happens, it means that something goes wrong and the model will not provide good predictions out of sample. But in case of ChatGPT, it actually consumes a lot of data, and this data is stored somewhere inside weights, and this data can be then extracted back. The second important thing with ChatGPT is that it can interact with people in a standard way using text, and with speech converters it can interact with speech. And also it can increase personal effectiveness. Because standard machine learning models, these are models for classification, for regression, they don't increase your personal effectiveness, but ChatGPT actually increases. And here is an example. Here is an example how it can do this. Because if we use ChatGPT to support coding, so this is an experiment from Microsoft Copilot. They take a group of people coding without LLM and with LLM, and the accuracy of coding, effectiveness of coding was comparable, but the time the second group with LLM spent on coding, it was significantly less. And so this is a clear indication of increasing personal effectiveness with large language model. And can it change the world? Can generative AI change the world? Well, possibly yes. It's always very difficult to make predictions, but in some sense the situation now with these technologies is the same as with old school internet in the 90s. This is actually the page from old internet, and many people thought about internet as a kind of a library where you can find some good book. But nowadays, internet is everywhere, and it actually, a lot of businesses originated thanks to the internet. So, and another indication is that this is the most profitable companies according to the US market in different moments of time. And actually among these companies, in 2023, the most of profitable companies are exactly companies in IT sector working with AI. And so all these things are kind of clear indication that yes, AI should change the world in some sense. Of course, it's difficult to predict how and when, but well, the race has just begun. And here are some trends, how it works. So first of all, if we denote with these symbols the situation with the technology we consider, like whether it is just at the research stage, whether it is already has a lot of users, or maybe it is already technology on the market that can be used for industrial applications. So we can clearly see that generative AI technologies that can mimic real video, real texts and sounds, these technologies are actually already kind of industrial, and they are already used in many different products, and there are many models working with text, with videos nowadays, and they are already introduced in some industrial systems for different industrial aims. What is the situation with other types of modalities? For example, the situation with, of course, smell and tactility is not so good. So this is only on research stage. Concerning CAD data and 3D data, the situation is, so there are some MVPs, some products where people use AI for modeling of CAD data, for example, for planning construction processes. And what is concerning the situation with video, well, currently there are many users of various video services, but still I wouldn't say that it is on industrial level. What's next? Yeah, concerning video, in 2023, there appeared around 10 or so generative models for generating videos. The generated videos were not of very good quality, but still they worked somehow. But in 2024, now we have already more than 50 different generative models for video, and I think that all of you have seen on the internet a lot of video clips of very good quality with corresponding generated sound, and already people are using these for video production, for advertisements, for making advertisements, and even making short movies. Actually, for example, recently even a whole film was produced where the robot grows. And what is important when producing this film, a usual price for producing 1 minute of such animation film is more than $10,000. But these people who used AI to work on this animation film, they spend around 5,000 or so, at least they claim this. The video from Sora and such models is very good already and can be used for various video clips for advertisement. And what is also important, thanks to some progress in modeling of 3D data, we can use these various 3D simulation environments to generate a lot of data, a lot of 3D data about our physical world, which is very important to train robotics. Actually, it's quite obvious that if we would like to train AI for robotics, so that a real robot can do something in a real world, we need a lot of labeled data, but it's not possible to produce such data. However, thanks to generated data, possibly we can train models based on generated data, and thanks to this generated data, we will train foundation models for robotics, and it should really help working with working in the real world. And of course, video games supported with generative AI, they can provide more interesting experience. Okay, these are kind of local trends currently with generative models, with models related to video mainly. And what is under the hood? Inside these approaches, there are techniques, very well-known techniques, such as generative adversarial networks, generative adversarial and diffusion models, flow matching techniques. These are probabilistic models used to model probability distributions of high-dimensional data of images or sequence of images which actually represent a video. And standard generative adversarial network, it works as follows. It's a neural network. Often it is a convolutional neural network. Nowadays, of course, we can use transformer architectures. So this neural network takes as input some IID random sample of Gaussian white noise. This is a very simple distribution. And then this sample is transformed nonlinearly into a high-dimensional vector which represents an image. And the quality of such generative adversarial networks is very high. However, the procedure to train, to tune parameters of this adversarial, of this generator is very, very heuristic. So there are a lot of different tricks, and these tricks are often not very well justified from a theoretical point of view. And so there is a clear lack of foundational mathematical understanding how this works and how to select architectures of such generators in some automatic way. Another standard model to work with images, or nowadays with video, is models based on diffusions. So this is also a very interesting approach. The standard model for diffusion generative modeling appeared in 2020. We train a special neural network which represents a diffusion equation, and it works as follows. So we train a diffusion to such that it can take as input any image from a real-world distribution of images, and then step by step it adds some noise to each pixel of the image. So after several steps, the image converges to just a pure white noise. And if we are able to construct such diffusion such that it can make any image as a noisy image, then we can revert this diffusion. So there is a special theory of stochastic differential equations. And from the theory, we can find an equation of a reverse diffusion. And this reverse diffusion, it works as follows. we generate a white noise image. That is, each pixel of the image is just a white noise. And then the diffusion starts denoising the image step by step, pixel by pixel, and finally it converges to something which belongs to the distribution of real images. And also we can guide this denoising process by some textual description. Actually, from a mathematical point of view, the problems we are solving using GANs, or diffusion models, these are problems of domain translation. In this school, there will be a series of lectures by Alexander Korotin and some other colleagues specifically devoted to domain translation problems. Domain translation problem can be formulated as follows. So we have some distribution, continuous distribution of real-world data, say P, and there is some other distribution, continuous distribution of real-world data, say Q, and we would, these distributions, of course, are not known, and we have only a sample of, for example, images from the first distribution and a sample of images from the second distribution. And based on these samples, we would like to construct such generator that can transform any new image from this distribution and convert it to a distribution as if it was generated by this, and convert it to an image as if this image was generated by the second distribution. In such way, we can formulate many different applied problems, like the problem of super resolution, image translation. For example, okay, this is of course a toy example, but I think it can illustrate the problem of domain translation quite nicely. Imagine that we have the sample of real-world image faces, and we have a sample of anime faces. Of course, there is no correspondence at all. And these are some real-world images of real faces as if they were generated by some distribution P. And this is the sample of real-world, the sample of anime faces as if they were generated by some continuous distribution Q. And based on these two samples, we would like to construct a generator that can convert any new real face image into the corresponding anime, so that we somehow keep the semantics of the face. And thanks to generative models, to GANs, to diffusions, it's possible to solve such ill-posed problem. Here is how it works. So for any new face, we can generate a random sample of anime faces, and we see that, well, semantically, this anime looks kind of similar to this real-world face. But the problem is that, as I said, with generative adversarial networks, the approach to train generative adversarial networks is quite heuristic. And the question is, are there any solid mathematical ideas how we can represent this problem in a rigorous mathematical way? And the answer is yes, there are such ideas. Actually, there was a very famous Soviet mathematician, Leonid Vitalyevich Kantorovich, and he is famous for many things. In particular, he is famous for mathematical theory of optimal transport. So the formulation of optimal transport problem is as follows. We have two distributions P and Q. And we would like to find such generator T, which transforms distribution P exactly to the distribution Q, such that the work, the efforts we spend for such translation is as small as possible. And we use these criterion to represent this kind of work. So in other words, we try to find such a transformation T that this transformation is as linear as possible. And actually, the optimal transformation T, or optimal map, can be considered as a kind of generator with such optimal properties. And this is exactly what we don't have in standard generative adversarial networks. As I said, instead, in standard generative adversarial networks, we somehow train generator that maps some simple distribution into some complex distribution. However, we don't, we just do some tricks and we don't guarantee any optimal properties of such generator. But from a mathematical point of view, it's always very important to have some optimal properties, and such formulation can be used to introduce strict, rigorous mathematical details into into a training process of GANs. Another question is, are there any similarities and differences between generative models based on GANs and generative models based on diffusions? And actually, of course, there are such connections. The problem of optimal transport by Kantarovich can be, of course, generalized, so-called weak optimal transport. Weak optimal transport is just a more general formulation of standard optimal transport problem. It means that we not only transform any point from one distribution Q, P to some point generated from distribution Q, because the problem of, for example, transforming such image into anime face is ill-posed, there are no exact correspondence, and because of that, it's better to consider a slightly relaxed formulation. That is, we transform image into some conditional distribution. It means that we, for any sample from distribution P, we can generate a bunch of samples conditionally on this X as if they were generated from distribution Q. In other words, we try to find such conditional distribution that minimizes this transport cost. So this is a more general formulation of the optimal transport problem. And actually, based on this formulation, we can train a more general version of generative adversarial network that works more efficient than standard generative adversarial networks. Moreover, in our recent paper, this paper, by the way, was accepted as oral to New RIPS conference in 2023, and by what is kind of interesting, by the scores, it was on the first place over all other papers submitted and accepted to New RIPS. So in this paper, we proved that there is a correspondence between weak optimal transport and diffusion models. So if we would like to solve weak optimal transport problem, then we should actually construct some special diffusion process, and it gives you the solution of the weak optimal transport problem. So this is the correspondence between these two types of generative models. So what I want to say is that behind the generative models, there is a very important, very interesting theory of stochastic processes, of optimal transport, of probability distribution modeling. And thanks to this theory, it's possible to construct new generative models to construct new algorithms. However, still there is a big challenge what mathematical models we should use in practice, because still now video generative models are not very computationally efficient, and still there are a lot of things to improve. Moreover, there are now good mathematical, theory whether these generative models are really accurate and how, with what speed do they converge. So still there are a lot of things to do for a researcher, for a mathematician, and in this school there will be a series of lectures by Alexander Karotin, who will discuss these questions. Okay, so now let me briefly remind what we discussed already. First of all, I presented some overview that generative models kind of will change the world in some sense, but I didn't explain why I think so, and now I will do this. And also I discussed that behind modern generative models for images and video, still there are a lot of challenges, I mean real mathematical challenges. And so if you guys would like to, to work with interesting mathematics, so this is your topic. And now let's discuss a little bit changing the world. AI agents. So I said that ChatGPT, or in other words, large language models, they can really work with text very, very well. We can use these models for different industrial projects, industrial problems. And what is important is that around any large language model, we can also add some additional algorithms, and we can turn this large language model into a reasoning model, into an agent that can not only generate text, but also it can plan its actions, and also it can reason. Reasoning is very important. If we want to solve a mathematical problem, we need to reason, we need to plan how we solve the mathematical problem, we need to plan the steps of the solution, and then we need to make these steps. And there are special algorithms for this, and the reasoning capability of large language models, these capabilities increase very significantly even in the last year. So on a very well-known benchmark for solving logic problems, these reasoning capabilities increased for almost 20%, I mean general efficiency. And this is kind of fascinating. And nowadays, even we can solve a kind of complex mathematical problems using large language models. Moreover, because a large language model can generate not only text, it can also generate a code. But generating code means that the large language model can be turned into an agent that is capable to interact with the external world. So we can add to a large language model some memory where it can keep its past actions. We can add to the large language model some reasoning capability, and also we can train the large language model to generate code to work in web browser, for example. And then, because of this, the large language model can solve your personal problems. For example, it can go to website and say, pass the automatic verification test. It can write in email instead of you, or nowadays already there are some services where you can buy some products just saying, okay, I want to buy shoes for jogging, the price is like this, please find me the best possible shoes, and then it just interacts with you, asks you questions, and then proposes you some solution to order. And this is a new way how we deal with external worlds. And for sure, in some short time, this should significantly change for example, the market of advertisement in the internet. Because, okay, nowadays, when we would like to buy something in the internet, what we do? We go to the web browser, we find on the websites the thing we would like to buy. And because of this, we, of course, make traces in the internet. And so, because of these traces, the web search engine can understand that, okay, we are a person who are interested in some specific goods. We do these actions, and then they provide to us some advertisement, and the companies pay for this advertisement. So this is the standard business of Yandex, of Google. But if instead of you, an AI agent does all these steps, the AI agent don't need to look at the advertisement from Google or from Yandex, right? The AI agent doesn't make such traces in the internet as people usually make. And because of that, it will significantly influence the market of advertisement in the internet, right? And the way how we interact with the external world, how we interact with the internet. And obviously, we can imagine a lot of different services powered by such AI agent. For example, instead of when we pay for our mobile phone, what we do? For example, we go into mobile app of Sberbank. There is a special button, pay for the mobile phone, and then we do some other actions, select bank card, etc., etc. But nowadays, but with AI agents, we don't need to do these actions. We just need to say to the mobile phone, I would like to pay for my mobile from Sber card 700 rubles, and that's it. And it can do this for you. And the actions are very simple. And your command set by voice, it can be translated into the sequence of steps by a large language model, and then the steps are done by the agent. That's it. Or web search or search for specific documents. With these capabilities, they of course will be significantly improved, these kind of services. For example, if you would like to find some patents on the internet, Google patent search doesn't work well. It will provide you a lot of kind of trash. But with if you perform ranking of the patents not only by keywords as Google does, but also if you do this with large language model, in this case, the ranking will be very, very good. So you just provide an example of the patent you need, similar patent. You maybe also provide some very, very short textual description, and then you can construct a very simple system of several agents, such that these agents rank the list of patents provided you by Google search engine, and then also they select the most important patents similar to what you really need. This really will change our experience with internet, with with interacting with different applications, and I think that this will happen soon. In principle, but what's about industrial applications, right? Here we were talking about some usual applications, what we really do each day, and what's about industrial applications? What's about how we can, in principle, describe these multi-agent systems? What is the next step of developing these multi-agent systems? And this is what we call engineering AI. We can say that, okay, AGI, well, nobody knows when an AGI will appear, right? And what is AGI? But clearly, the next development step of AI is, so the first step was, the previous step was kind of artificial narrow intelligence. Narrow in the sense that each AI model, it was doing some particular step. For example, classification, semantic segmentation or something. So very, very particular thing. But nowadays, with these multi-agent systems, we can imagine almost fully automatic solution of complex engineering problems. Why? It's because we can divide the complex engineering problem into a sequence of steps, and then each step is done by a specific agent. And why is this possible? This is possible thanks to large language models in particular. In 80s, large language models were, they were very, very simple. In 80s, of course, there were probabilistic models for working with texts, so-called symbolic AI. And people think that symbolic AI very soon will turn into AGI. But of course, this didn't happen. Current large language models actually can breathe a new life into symbolic AI. And symbolic AI is very, very important because it can really it can be really used to plan actions. It can be really used to divide the complex problem into smaller problems. And this is what is really needed for industrial applications. In order to test the efficiency of multi-agent systems, it's very important to imitate real-life conditions. And games is a very, very good way to imitate real-life conditions so that we can evaluate properties of multi-agent systems from different aspects. From the aspect of whether they can plan efficiently, whether they can reason efficiently, whether they can memorize information efficiently. And now I'd like to briefly overview some interesting results about how we can evaluate, how we can construct a multi-agent system based on just pure large language models, which can interact with external world. And this external world, in this case, is given by a textual game. Textual game, actually, here there are a lot of young people, but still you guys who are a little bit older may remember that in the 90s, textual games were very popular. Textual game means that you get a textual description of a particular, situation in the game. For example, there are many rooms, and you can go from one room to another. And in each room, you can perform some actions, and you need, say, to find some specific item. And then you need to bring this item into some other room and do something else. And each step is done by some action from a given list of actions. And once you make this action, then the game generates the next step. It generates the next situation. and everything is described in text, right? And if we just take a standard large language model and ask the large language model to play with such game, it will fail. Why? Because in order to play with such game, you need to remember the past steps, the previous steps. And even if your large language model has a long context, even in such case, it will fail quite soon, so it will forget very soon about the previous experience. And the question is how to construct a multi-agent system that is capable to keep memory about the previous steps. It can update the information from the previous steps, given information from the current step, and such that it can plan its future actions. Of course, we can add to such language model standard engineering tricks like, long context, or, for example, we can add retrieval augmented generation that is based on vector database, or we can provide some summary of past actions. And, well, this will help a little bit to increase efficiency. In our recent work, we propose another scheme how to deal with such situation. Namely, we developed a very interesting mechanism of the memory. And so this memory consists of two parts. The first part is episodic memory, and the second part is semantic memory. So these two types of memories are actually these types of memories we have. We have the memory about events, like regular events. Okay, we come into room, we drink some cup of coffee. So these are some events. And then, under some conditions, these events are grouped together to form our memories. And these are two types of memories, some particular events and groups of events that can be considered as some important thing happened with us. And actually, this thing can be represented, and this memory can be represented as a knowledge graph. Each node in the knowledge graph, it is a particular event happened with us. And groups of nodes, these are groups of events that happen. For example, today we have a big event. We opened our school, but this big event, it consists of small events, small sequence of events. We came to Harbin, we came to the hotel, we do something else, and we can actually, and also between these events there are dependencies, there are connections. And of course this information can be represented as a knowledge graph. The same we can do in our case, in case of a computer game with text. We can ask a large language model to construct a semantic memory. So as soon as we get some textual description of a particular step, we extract with large language model with some prompt important objects from this textual description and connections between these objects. And then if semantic memory is too old, we also can ask large language model to update semantic memory as soon as we get some new information. And so we can replace with instructions some part of the semantic memory using large language model. And also the sequence of events can be grouped into episodic memory. This also can be done with the large language model with some specific instruction. And as soon as we organize our memory into a knowledge graph with such structure, we can use it to support our decisions. So as soon as the large language model should plan some next action, we ask the large language model that it should also go to the knowledge graph and extract the relevant information from the knowledge graph. This is the example of the knowledge graph constructed for some particular textual game. So you see different nodes, different connection between nodes. And based on these ideas, we constructed a multi-agent system. It consists of several language models with different prompts. Some language models are used to construct a memory, to update a memory, to update the memory, to add some new information or delete old information. And another language model is used to plan actions based on this memory. And it turned out that this language model, this multi-agent system, it works very efficiently compared to even humans. So we tested it on a number of textual games, and here is a comparison. So this first column is the average efficiency of the multi-agent system working with these textual games, and this is top 3 players. And you see that actually compared to top 3 players, the performance of this system is almost the same. And if we use standard language models with standard capabilities like memory based on long context or memory based on reg capability, well, they're not so efficient. Okay, these are some plots representing how the system converges, and you can see that if, for example, this is a particular game here, cooking. Cooking means that we need to go from one room to another, find some specific product, and cook something. And the convergence of the algorithm to top performance given by the red curve is exactly our approach. And all other approaches, they converge very, very slow. So this is a clear indication that a system with such memory is very efficient. And this, of course, can be used into different scenarios. For example, we can use this for question answering. It means that when we construct such question answering system, one language model will be used to extract information from documents, and another language model will organize this information in the form of the knowledge graph, and another language model will be used to generate answers. And it turned out that such approach, very simple approach, we even don't train, we even don't fine-tune large language models for this data. It turns out that, well, this works very well even without fine-tuning. So the performance, the performance of our system is given here, and it's of course not as good as the performance of some other systems, but these systems were fine-tuned on this data, and our system, it wasn't fine-tuned. We just used it without any fine-tuning, just took several large language models and used the ideas I presented, and that's it. And so there are a lot of different applications how we can use these in practice, these ideas. We can use it for personalization. We can use it for domain knowledge memorization, for visual navigation. So we can use it for different kind of things. In particular, what is engineering AI again? Engineering AI means that we, of course, have some domain, subject domain, for example, oil and gas, or design of complex mechanical systems, or design of complex buildings. And in each of such domains, there are a lot of important information which should be somehow organized. We can use we can extract this information from documents, we can extract this information from papers, and organize this information as a knowledge graph. Also, there is some, orchestrator. This is an agent which takes our, our problem, decompose it into steps, and then it constructs a sequence of agents which perform these steps. And this is a clear, this can be clearly represented as a multi-agent system supported by such memory in the form of the knowledge graph. And there are a lot of industrial applications which can be realized in such way. For example, recently we already developed an application for so-called oil and gas reservoir modeling. Oil and gas reservoir modeling means that we have oil and gas deposit. There are a lot of information from about the oil and gas reservoir, such as seismic data, hydrodynamic data, geological data, and we need to predict oil and gas production. And so, using multi-agent system, we can construct a computational process automatically that takes this data, constructs estimations of different characteristics across oil and gas deposit, like porosity, permeability, and other characteristics, and then use these as some model of oil and gas deposit, and then using multi-agent systems, we fine-tune this model to predict oil and gas production. So actually, we already developed this approach, and it works very well in practice. It produces really quite physically looking models of oil and gas deposits compared to models produced manually. So this is already a very good example of how we can use multi-agent systems in industrial processes. Currently, we are working on generative design, and so in this school there will be lectures of Andrei Kuznetsov. He works in Sber and AIRI. He will discuss some aspects of generative design as well. And problems of generative design, they also can be represented as a sequence of actions, and we can automate these by using multi-agent systems. What is also important is that for industrial processes, there are a lot of technical documentation. And again, multi-agent systems is a very, very important and good tool for automation to extract information from this technical documentation, so that we can take a big database of various technical requirements, of various restrictions and technical restrictions, and then we can construct a knowledge graph how different different objects, different restrictions are related to each other, and this can be used to automate recommendation for engineers when they plan design of complex mechanical systems and buildings. And of course, this can be used for modeling of socio-economic systems because, okay, all of us generate a lot of data, and this is, based on this data, we can construct multi-agent models to mimic our behavior, and this is very, very important for planning and optimization of socio-economic systems. So, as a conclusion, I would like to say that, well, large language models are not AGI, of course, but, it's not very important when we achieve AGI. It's very important that already now we have a very good technical capabilities using which we can solve complex engineering problems more efficiently than ever. And the next step I kind of was presenting today is automation of solving these problems based on multi-engine systems, so-called engineering AI. And there are a lot of applications behind this. So would be happy if you join our team and work with us in solving these important problems. This is some used sources. So I use to make this presentation, I used different sources. Yeah, this is the reference to the paper, to our recent paper accepted to A-Star conference in Chicago about multi-agent systems with knowledge graph. And so there can be different ways how you can apply in practice this methodology. And this is some my personal contacts in Telegram and WeChat, of course. And also this is a Telegram channel of our center, so some recent news on AI you can find there. Well, that's it. Thank you very much. Questions? Any questions? Yes, please. Microphone.
Thank you. Could you please advise to what extent planning is really useful in this? What I met in practice is that the people who design the logic of the steps, usually they're expert in this journey, and usually they know much better than the LLM does, right? So they, it's not like they say like, you plan what steps I should take. It's more like, these are the steps that you should perform, and this is just the decision, the context you need at each step in order to make a proper decision, in order to go to a right direction at each step. So to what extent planning is really LLM designed rather than human designed?
Well, this is a very, very good question. Could you please put slides back? Yeah, thank you. I just wanted to remind you this scheme. I understand that this scheme is a bit kind of, not so easy to understand. But what I would like to draw your attention to is this knowledge graph, kind of information from subject domain. For different domains, this information should be collected and organized as a knowledge graph in U. It means that in our experience, for example, for oil and gas, we did some interviews with experts from the field. They tell us, okay, if you have this data, then in order to convert it into another form of data, the better option is to use this software or is to use this formula. And so we, after these interviews, we constructed a big knowledge graph containing this expert knowledge. It was kind of not so easy job, but it took us around maybe half year, but it's doable. And for this domain, you can use this knowledge graph when you solve the same problem many times, you don't need to go to expert and ask them question. You already have everything inside the knowledge graph, and based on this language model or orchestrator, it may be not a language model. It may be some other algorithm. So based on this knowledge graph, it can plan its actions without experts, because all information is already inside. Concerning processing of documents, you also can construct such knowledge graph. But what is important, instead of interviewing experts, you can automate construction of the knowledge graph by using LLMs again. So using large language models, you can extract objects from documents, you can extract relations between objects, and you may just need after that to check the result, but that's it. So in many cases, even construction of such subject domain knowledge can be automated. And then you can use it repetitively when you solve similar types of tasks.
Yes, but what about planning?
Yeah, but concerning planning, it depends on the domain. But say, based when you have this graph, okay, you have, for example, in oil and gas, you have this specific type of data, right? Say you have about the data, about the oil and gas, you have some seismic data. And then you go to knowledge graph and see, okay, if you have seismic data, from seismic data I can make these predictions, I can calculate this, and it gives you already an approximate plan what you should do. So from knowledge graph you already extract a road, a particular sequence of steps which you should perform in order to calculate what you need. Because experts already told you how to calculate one type of data, one type of predictions using another type of, using the data you have.
So in a sense, planning steps are embedded in this knowledge.
In case of oil and gas, they are already there. In case of, for example, processing of documents, it's another story. In case of documents, you the graph contains, the knowledge graph contains information how different, technical restrictions, objects are related to each other, and then language models are used just to verify this information or to generate answers to questions, etc., etc. So this is another thing. So you don't need to plan in that case. So it depends. Yes.
Yeah, thank you very much for the lecture. I have one question. You mentioned that LLM models thinking have its roots in symbolic AI, which was developed several
Decades.
10 years ago. Yeah. What can you recommend some alternative approaches to the thinking, and maybe some alternative logic?
Alternative approaches to what?
To thinking.
Well, it's a general question. So by this slide, I just, wanted to say that there are different types of, approaches to AI, and some of the approaches, old approaches, people forgot about them, but what we already have now, they're kind of new reincarnation of what we used several decades ago. But because of new technologies, new computations, nowadays we can kind of give a second life to symbolic AI.
But what are the next steps?
Well, the next step, as I said, we can combine now symbolic AI and narrow AI into multi-agent systems, and this gives us new possibilities.
No, just asking about new steps in thinking. Are you optimistic about human language, so that everything in the space can be explained and logically done in human language?
Well, it's too general question. Maybe there are things which we cannot understand, right? And because of that, they cannot be explained by human language.
So I simply ask, is there any alternative approach of applying thinking in LLMs rather than symbolic AI?
Well, of course, it depends how you encode reasoning, and this is a challenging problem. What language we should use, for example, to encode mathematics in order for LLM, LLM will be more efficient when solving mathematical problems. This is a big problem now because the current language used to encode mathematical problems is not so efficient and easy to be used with large language models.
Okay, thank you very much.
Thank you very much for so nice talk. I'm sure that future belongs to graph approaches.
Knowledge graph, I was talking about it.
Yeah, I have a little bit speculative question. How do you think how important in perspective would it be to create artificial consciousness, and whether knowledge graphs or ARI graphs can be the way to it? Because recently in neuroscience, actually, there were several papers showing that human brain are using graph transformers and probably ARI graphs in their function. But do we need this?
Well, do we need this? It depends on, from my, I solve a lot of engineering problems. And from my point of view, if you invented something, some mathematical concept, and if it allowed you finally to solve even more complex problems, engineering problems, well, then this concept is useful. If not, then you don't need to use it. Concerning your question, it depends. If you would like to explain somehow mathematically processes in our brains, it's one story. Maybe we need graphs for this, maybe not. It depends. I don't know. But if for engineering problems graphs are useful and we see that they are useful, then we should use them. Yes, please.